Hi everyone, welcome to 7 Places Introduction to Chemistry and Cookies, and this is day 2, part 2. All right, well, let's get into it, I guess. So we have discussed briefly the two types of bonds that there are in chemistry, ionic and covalent bonds. You guys might remember this from day 1, I believe it was. So in ionic bonds, one atom gives one electron or multiple electrons to another atom. So for example, because remember, all atoms want to have a full outer shell, right? They want to have 8 valence electrons. And so in this case, for example, sodium has 1 extra valence electron that it wants to get rid of so that it can have a full outer shell of 8. And chlorine has 7 valence electrons, so it wants 1 more so it can have, again, a full valence shell of 8. So this electron right here, represented by my laser pointer, which hopefully you can see, from sodium is going to go over here and become this electron for chlorine. And then because of that, sodium and chlorine will both be happy because they both have a full outer electron shell. Also because of this, sodium is going to have a positive charge because it just lost an electron, and chlorine a negative charge because it just gained an electron. These two charges are going to attract each other, and that is an ionic bond. It happens between a metal and a nonmetal because metals such as sodium want to lose electrons usually, and nonmetals such as chlorine usually want to gain electrons. So it kind of works out neatly there because metal loses and then nonmetal gains and everyone's happy. These are also stronger than covalent bonds, which are electrons, which is when electrons are shared between atoms. So for example, oxygen has, in this scenario, 6 valence electrons and wants 2 more. This hydrogen has 1 valence electron and wants 1 more, so it can complete its outer shell with 2. And same happens for this hydrogen. So oxygen and this hydrogen will be sharing these 2 electrons, and then oxygen and this hydrogen will be sharing these 2 electrons. So what happens is that oxygen now has a complete valence shell of 8 because it has its 6 original electrons plus 2 new shared ones, and each of the hydrogens will also have a complete valence shell of 2 in their case because they have, oh, that's not good. Okay, there you go. Because it has, they have their original electrons plus the new shared electron that they're sharing with oxygen. And these are between 2 nonmetals because nonmetals, as I mentioned before, usually want to gain electrons. And since both use the electrons that are shared, they both have a full shell. So basically, both oxygen and the 2 hydrogens are happy in this scenario, which is water, by the way. And this is table salts. So, okay, well, that's interesting, right? But then we mentioned in the previous video for day 2, part 1 about electronegativity and how it affects how much an atom can pull a shared electron to itself. Okay, so if covalent bonds are just sharing electrons, why does that matter to us? Well, because even though covalent bonds, are sharing electrons, they're not sharing them equally. So, for example, we can have basically polar or nonpolar covalent bonds. So what this means is, for example, we have here 2 hydrogens, right? They're sharing, this hydrogen has this electron and is sharing this one, and then this electron originally belonged to this one, and they're both basically sharing 2 electrons, so they're both happy. Well, if we look up hydrogen's electronegativity, it is 2.2, which isn't something, again, like I had to look it up. It's not something that you just, like, I mean, you could memorize it, but I wouldn't expect you guys to know it. So this has an electronegativity of 2.2, and this other hydrogen also has an electronegativity of 2.2. So where do the electrons want to go if they want to go to the bigger number? Well, if the 2 numbers are the same, as is clearly the case here, they have the same electronegativities because they're atoms of the same elements, then the electrons are going to be pretty equally shared. They're not going to go more to this one or more to that one, they're just going to be equally shared. So as you can see here, nonpolar bonds, covalent atoms will share the electrons equally. Or here, wait, it's probably going to be a little bit clearer if I do this. There we go. And that only happens if the two atoms have similar electronegativities. In this case, the electronegativities are obviously the same, but if it were, for example, like 2.2 and 2.4, that could probably still be a nonpolar bond. Or if you had an electronegativity of 2.2 and one of 2. So again, similar electronegativities, basically a nonpolar covalent bond, where electrons are shared equally. But sometimes electrons aren't shared equally, as is the case in a polar covalent bond. So we have here 2 hydrogen atoms and then 1 oxygen atom. So the hydrogens have an electronegativity of 2.2. We know this because we already looked it up. We saw it here. And oxygen is going to have an electronegativity of 3.44. And these numbers are just like, they're available online. You can just look them up and you'll find them basically. Okay, so we have this electron pair that is being shared between oxygen and this hydrogen, and we have this electron pair which is being shared between oxygen and this hydrogen. Remember, the electrons want to go to the bigger number, and 3.44 is clearly bigger than 2.2, and since this is also 2.2, 3.44 is still bigger. So this electron pair right here is still going to be shared, but it's going to spend more time with oxygen. And this electron pair right here, which is, again, not being shared between these two, this pair is actually being shared between these two, is also going to want to go more towards the 3.44 than the 2.2. So they're still being shared, but oxygen has them, we can think of it like the hydrogens only get the electrons on weekends versus oxygen gets them weekdays. So oxygen has, which isn't what's happening, it's just like an analogy. So oxygen has them kind of for more time, or pulls the electrons more toward itself. So we can kind of say, it's not really what's happening, but we can kind of say that oxygen has 8 electrons and that the hydrogens each have 0. Like if you were to ask, oh, where do these electrons prefer going? It's going to go to the oxygen. So that gives oxygen a kind of negative charge because it just gained 2 electrons that it didn't have before. Again, it's not really gaining these electrons, they're being shared, but like, for example, if this is a rope and oxygen has one end and hydrogen has the other end and the electrons are on it, they're not going to be in the middle, they're going to be like over here. And same with this, right? It's like, oh yeah, here's a rope and we're going to share the electrons. So we just put the electrons on the rope and there they belong to both of us. But they're not going to be in the middle. They're going to be like way over here. So what happens is that oxygen, because it kind of pulls the shared electrons more towards itself, is again going to have a partially negative charge. And we write it like that. This is, it's a very poor drawing of me attempting to draw delta. And then the hydrogens are each going to have a partially positive charge because they are not really losing electrons, but they're kind of losing electrons. When before they had 1 electron all the time, now they have 2 electrons, but only like one, every once in a while. So they're kind of positive. And so this is what we mean by when we say that in a polar bond, covalent molecules share electrons unequally because they are more pulled to one atom than to another atom. So here they're more pulled to oxygen than to the hydrogens. And this happens when atoms have different electronegativities, because we have to remember that electrons will be more drawn to higher electronegativities. So we said the oxygen has 3.44, hydrogen has 2.2, so they're going to go to the 3.44 that is the electronegativity of oxygen. All right, and now we're kind of switching gears a little bit, and we're going to talk a bit about mixtures versus solutions. So they are kind of similar in the way that they both have to do with putting things together. So it can be sometimes a little bit confusing as to whether something is a mixture or something is a solution. But here are a few key points to kind of help you differentiate them. In a mixture, two or more substances are mixed, but they are not chemically combined. So mixing things together is kind of like, or well, let's actually go over solutions first. And solutions occur when a substance is dissolved in another substance. So this actually forms a new substance. Okay, so here we have, it's kind of, if we have, for example, a bunch of marbles and we put them together, we have some red marbles and some blue marbles and we put them together in a bowl, we can still see the red versus the blue. We can separate them pretty easily. They're not dissolved in each other. They're just, they were apart and now they're together. Versus solutions is more like if you grab sugar or salt and you dissolve it in water. It's going to be really hard to separate it out. You can't see the salt versus the water. Now they're just both together in salt water and something dissolved in something else. So in mixtures, each substance keeps its original properties and characteristics. Like, again, if you were to put two groups of marbles together, they're not going to change color, they're not going to change shape, they're not going to merge, they're just going to kind of sit together. And because of this, mixtures are more easily separated. If we grab, I don't know, like a bunch of straws and we put them in a bowl with different colored straws, we can easily pull out, they're easily separated basically. Sometimes these are called heterogeneous mixtures, and we call them this because hetero equals different, and that basically means that the mixture is different throughout. Like, for example, if we were to grab a bunch of soccer balls and marbles, right, and we put them together, the soccer balls are really, really big and the marbles are really, really small. So if we put them all in a bucket, the marbles are all going to go to the bottom and the soccer balls are kind of going to like bump into each other and they're not going to be able to drop as easily. So that means that if we were to grab a little sample from the mixture from the bottom, we would have more marbles, versus if we were to grab a sample from this mixture from the top, we would have more soccer balls. So it's different throughout, basically. And some examples of this are cereal, salad, oil, and water, which, because I don't know if you've ever done this, but if you grab oil and you grab water and you put them together, the layers will separate. There is a clear layer of oil and a clear layer of water. And that's actually because oil is nonpolar and water is polar. We actually saw the water molecule. That was our example for a polar molecule. And polar and nonpolar don't like to mix. They prefer to kind of stay separate. So if you put nonpolar oil and polar water together, they will not dissolve in each other. They are going to very clearly separate. And as opposed to solutions, they are spread out evenly. By which I mean, if you were to grab a sample of salt water from like the bottom of the cup versus the top of the cup, it's going to be the same concentration of salt versus water. And because of this, they're called homogeneous mixtures. In this case, homo meaning same because, don't know what happened there, because it is the same throughout. And some examples of this are sugar or salt dissolved in water. Again, the sugar totally dissolves in the water and you're not going to be able to see sugar versus water anymore. Lemonade and Kool-Aid. Usually when we think solutions, we think liquid. Like if we have like a solid dissolved in a liquid or something like that, but it doesn't have to be. There, for example, you can dissolve gas in a liquid. There's just a bunch of different ways that can work, basically. All right, so here we have some practice, whether it's a mixture or solution, and I'm just going to wait for a minute. You can try to figure it out, and then I will be back in a minute. All right, well, hopefully you were able to kind of start figuring these out, and now I'm just going to go over them. All right, so first up we have sand and water. If you put sand and water together, the sand is going to kind of sink to the bottom, and the water is just, it's not going to dissolve in the water basically. So this is going to be a mixture. Salt and water, on the other hand, we actually did talk about this. The salt will fully dissolve in the water, and it's going to be the same throughout. So this is a solution. Now we have tea. Well, if you think about tea and you try to kind of differentiate kind of the tea from the top versus the tea from the bottom of a glass, it's going to be the same. So tea is a solution. Ice in a drink. If you have, for example, like a glass of soda or something and you put ice in it, you can clearly tell the ice versus the soda. And it's not going to be the same throughout, so this is a mixture. Of course, this is assuming that like the ice isn't melting, it's just ice versus liquid, and it's pretty easy to kind of separate them out and see what's what. Salt and pepper, if you were to put salt and pepper together, you could see the salt, you could see the pepper, and you could separate them out. Kind of difficult, but you could do it if you really tried. So this is a mixture. Whipped cream. Well, okay, this is kind of a tricky one, but if you really think about whipped cream, it's kind of like, it's not necessarily going to be the same throughout. So this is a bit of a tricky one, but it is actually something called a homogeneous mixture. So what this means, we talked about homogeneous in terms of solution, and that means that it's the same throughout. But in whipped cream, there's nothing actually dissolved in anything else. So whipped cream is actually going to be a mixture, but it's going to be a special mixture in which everything is the same throughout. So that was a bit of a tricky one. And then we have vinegar. I don't know how familiar you guys are with it, but if you think about it, it is going to be the same throughout, and it is a liquid, so that kind of clues you in as well, although that's not always the case, but vinegar is a solution. And then we just have some true or false questions. All solutions are technically mixtures. Well, if we think about it, a mixture is two or more things together that aren't necessarily a chemical reaction, and a solution is something dissolved in something else. So this is actually true because mixtures are just two or more things versus solutions are two or more things that are dissolved in each other. So all solutions are mixtures. However, when we get to all mixtures are solutions, we can see, for example, that sand and water is not going to, the sand is not going to dissolve in the water, but that's still a mixture. So this is going to be false. So it's kind of like how all squares are rectangles, but not all rectangles are squares. Well, all solutions are mixtures, but not all mixtures are solutions. Now we're going to just go briefly over some laws of chemistry because they do exist and they are important, especially for our experiment that we're going to do in a second. So we have the law of conservation of mass. So this says that mass, that's another one. Mass is neither created nor destroyed during chemical reactions. So this basically says mass is not created, mass is not destroyed during chemical reactions. So what does this mean? Well, we have a constant mass in the universe. We can't create new mass, we can't destroy mass. So the amount of mass is always going to stay the same. And this also means that the weight of the reactants, mass has to do with weight. So for example, we have in grams or kilograms. So the weight, the mass of the reactants is going to be the same as the weights of the products in a chemical reaction. So that's actually going to be pretty important. So if you have, for example, a bunch of wood and it weighs 100 kilograms, and then you burn it, and you measure the weight of the ashes, but also the gases that were released during the chemical reaction, the ashes plus the gas is going to weigh exactly 100 kilograms, which is what the wood weighed. So can't create mass, can't destroy mass, and weight of reactants and products is going to be the same. Now it's time for one of my favorite parts. So this is the cookie application time. So let's think about mixtures versus solutions. So we have butter, right? One of the ingredients in cookies. Do you think it's a mixture or a solution? Then we also have flour and sugar together. Would that be a mixture or a solution? And then also we're going to think about mass conservation. Have you noticed that cookies lose weight in the oven? A spoon of dough weighs more than the baked cookie, but why? And I'm just going to wait for a second. You guys can pause the video and kind of try to solve these. All right, well, hopefully you guys have kind of thought about these for a little bit. So we have butter, right? Butter is, it can be a bit tricky if we don't know a lot about butter, which is why I have this here. So butter is actually a special type of mixture called an emulsion. Why isn't this going away? Oh well. So remember how I said that oil was nonpolar and water was polar, and that because of these they didn't mix? Well, they don't mix usually, but milk and butter are special cases. So an emulsion is basically a mixture of two things that don't usually like to mix, like polar and nonpolar substances, in this case, oil and water. Milk is actually an oil in a water emulsion, so that means that there's a little oil and a lot of water, and they're kind of together even though oil is nonpolar and water is polar. Butter, on the other hand, is a water and oil emulsion, which means that there is a lot of oil and a little bit of water. Or, I mean, that is to say, there's more oil than water. And that is because, butter comes from milk, but it is a dairy product. So that was a bit of a tricky one, but it is actually a weird emulsion type thing. Flour and sugar is a bit easier. If we have flour and sugar together, they don't dissolve in one another, and it is possible to separate them, even though it's going to be kind of tricky because they both look similar. So this is actually just going to be a mixture. And yes, so mass conservation. Have you noticed that cookies lose weight in the oven? A spoon of dough weighs more than the baked cookie, but why? Well, this has to do with the law of mass conservation, and also something that we don't usually think about for chemical reactions, which is gases as products. Cookies have multiple reactants that have, for example, water in them. We have butter, which has water in the oil. We have multiple chemical reactions happening. But when you put something in the oven and you put it at a very high temperature, I know that, for example, some cookies need to be baked at like 400 degrees Celsius or, Fahrenheit or something like that. And at that temperature, water evaporates. So, well, I mean, it has evaporated already. So what that basically means is that one of the products for the chemical reactions that happen in the oven for cookies is water vapor. That is, it is water, H2O, but it is in a gaseous form. So since the law of mass conservation tells us that the mass of reactants has to be the same as the mass of the products, and gases are products of some of the reactions that occur, that means that the cookies appear to lose weight because some of the products kind of float away. You know, when you get a spoon of dough and then when you get a finished cookie, you're not, and you weigh them against each other, you're also not weighing part of the products, which are the gases. So basically, the law of mass conservation is still in effect. It's just that we don't see or we don't count some of the products when we weigh a finished cookie. All right, and now it is experiment time. This is a pretty easy experiment. You can also do it at home, but it is extremely important that we learn how the experiment works before we do it. Please listen first, and then when the video is over, you can try it yourself. But again, you have to kind of learn what we're doing and why we're doing it before you can start doing it yourself, just as a safety thing. Things that we'll be using are vinegar, baking soda, a kitchen balance or some other tool to weigh, a bottle of some type, and a balloon. Or instead of a bottle, just any closed container, basically, or any container that you can close. So we're going to have two systems. We're going to have an open system and a closed system. For the open system, we're just going to leave a bottle open, kind of, basically, you know, making it open. And then we have a closed system where we're going to put a balloon on top of the bottle to make sure that the system is closed. So this is a video of me doing the open system. So just, hi everyone. So I'm going to be filming today the conservation of mass vinegar and baking soda experiments. So the original plan was to do it live over Zoom, but we thought that, you know, with camera angles and such, it would be easier if we filmed it beforehand and then showed it to you. So, are you guys ready to do an experiment that will prove the law of conservation of mass correct? Well, hopefully you are. So what are you going to need for this? Well, you're going to need some vinegar, some baking soda, some type of plastic bottle. So this is a 2-liter one. I find that works well. But if you have a smaller bottle, that works, that works great too. Just make sure that you use less vinegar and less baking soda. You're also going to need something to measure weight. So this is a kitchen scale, a kitchen balance. If you have a scale, that works too. And you're also going to need something to write with. I'm using a whiteboard, but paper and pencil works just fine. So we are going to grab our bottle and we are going to put some vinegar in. So you don't want to put too much vinegar because that will actually, the experiment won't work as well as you plan. So this is just maybe, just a little bit of vinegar, maybe 1/3 of a cup. So it only reaches like down here. You really don't need a lot. Just put in very little vinegar and you'll be fine. Then I have some baking soda. This is about 1.5 teaspoons of it. So we're just going to weigh everything, just like that. And we're going to record the weight. So this is 355 grams. So I'm just gonna write that down. And then after you have weighed it, you can just go ahead and put the baking soda into the vinegar. So you can see that this is starting to bubble up. It's also emitting a very strong odor. You can see the gas bubbles rising. And if we see here, we actually have 351 grams. So the mass went down. We started out with 355 grams, now we have 351 grams. And if we were to leave this for longer, the weight would actually continue to decrease. So why is that happening? Why is the weight going down? So yeah, you can kind of see the reaction between the vinegar and baking soda happened there. And here we have some discussion questions. And something that, I mentioned in the video, the mass went from 355 to 351 grams. So we lost a whole 4 grams. But how did that happen if the law of conservation of mass told us literally that we could not lose weight? Well, here is the chemical equation for the reaction that happens between baking soda and vinegar. This here is the baking soda, which you can see is a solid. This is the vinegar. And the products are carbon dioxide gas, liquid water, sodium ions, and CH3CO minus, also an ion. So what are the reactants in this equation and what are the products? Well, and feel free to pause the video and kind of think about this yourself. Well, the reactants in this equation, here, are going to be to the left of the arrow, so they're going to be the baking soda and the vinegar. And the products are going to be on the right side of the arrow, so that's what was formed basically. So we have carbon dioxide gas, liquid water, and then our ions. Why did the bottle lose weight? Well, that's something really to think about. But remember how I mentioned previously that cookies lose weight when you put them in the oven, or appear to lose weight, because one of the products is a gas. And here, if we look closely, we can actually see carbon dioxide gas as a product. So that means that we had a gas as a product, and this means that part of the products were not counted when we weighed the bottle, because they kind of just drifted away because the bottle was open. And what do you think will happen if we put a balloon on top? Well, I guess we're gonna see what happens, because that's the next video. So make your guesses now. Hi guys, so this is part 2 of the conservation of mass lab. So for part 1, we did an open system. We just left the bottle open, uncapped and everything. And we saw that the mass actually went down. The weight actually decreased. So that was something interesting. Now we're going to try something a little bit different. We're actually going to close the system up using a balloon. It's just like a standard party balloon. And so what that's going to do is we're going to seal the bottle, and nothing's going to be able to get in or out. So that's going to be interesting. So I have washed my plastic bottle. If you have 2, obviously you don't need to do that. Now we're just going to add some vinegar to it. So remember, you don't need to use that much. You need to use maybe like 1/3 of a cup of vinegar only. If you were to use too much, then nothing would happen, but the experiment might not work as well. And also the bubbles might go over, so that's a tad messy. We can just ignore that part. So we're just going to put about 1/3 of a cup of vinegar into the bottle. So again, that's really not a lot. It goes up to like maybe here. Then rather than putting the baking soda in here, we are actually going to put the baking soda into the balloon. So you may want to use a funnel for this. I know that it can be a tad tricky, but just have a little bit of patience and eventually you will fill that balloon. There we go. So now we're going to put the balloon over the mouth of the bottle. 2 very important things. 1, you want to make sure that the bottle is completely sealed, because if the balloon has any holes, or if you don't put it correctly, the experiment isn't going to work. And 2, we don't want the baking soda to fall into the vinegar just yet. If that happens, then the chemical reaction is going to start too soon, and then we're not going to be able to get all the measurements we need beforehand. So just carefully put the balloon over the mouth of the bottle, like that. Just make sure that there are no holes anywhere. There you go. Now we are going to weigh it. So if we see here, this weighs 155 grams. So I'm just going to write that down so we can compare it against the weight after the reaction happens. So is the balloon going to, what's going to happen to it? Make your guesses now. Okay, so I am just going to pour the baking soda in. We're seeing some really nice bubbles. The balloon is actually inflating. When you look at that, it's getting bigger. Just going to leave it for a little bit. And then if you look at the weight, it's actually still 155 grams. The weight has not changed. So that's something interesting to think about. I'm just gonna write that down. And yeah, interesting thing to think about. When we seal up the system, the weight does not change. So that means basically, again, weight is basically mass. So why did the mass remain the same when we sealed up the system? Well, because now we are counting the gas, basically. Because beforehand, the carbon dioxide gas kind of floated away and wasn't counted in the weights. But when we seal it up with a balloon, it has nowhere to go. It's kind of trapped inside. So it accounts, it is weighed as part of the mass for the products. And why did the balloon inflate? Well, that once again has to do with our friend carbon dioxide. Let me just write the subscript like that. Because the carbon dioxide gas drifts upwards and that was able to inflate the balloon. So yeah, pretty cool experiments. Now it's time for you to do it if you are so inclined. Here are the steps for the experiment. You can, screenshot this or something. And feel free to tell us how it went in the comments. Well, that's all for today. Hopefully you enjoyed.